Well, hello and welcome to the lesson 22-2 practice on page 311 in our text. Item 12 says use a calculator to find each of the following and round each value to the nearest 100th. So if we break this down, it's a pretty simple task. We are asked to find the sine of 48 degrees. Now, most of you won't have a graphing calculator handy, so I'm going to make sure you know how to use Desmos to do that. So if you go to desmos.com, click on graphing calculator, the first thing they ask us to do is to find the sine. So I'm going to type in SIN, sine of 48. And so we get this long decimal here, which is 0.74, and they ask us to round to the nearest 10. So it would be 0.7. So the sine of 40, they say 100, so let's correct that. So the first decimal place is called the tenths, the second decimal place is called the hundredths, which the 4 is in the hundredths place. So to round to the hundredths place, we actually look at the thousandths place, which is the 3. And the 3 tells us to keep that 4 the same. So the sine of 48 degrees, rounded to the nearest hundredth, is 0.74. Now, I do want to remind you, because it's a pretty simple task, what's really happening here. We're saying if we have some right triangle, and again, these trig ratios only exist, or for now, the way we're going to look at them, in right triangles. We're saying if we have a 48-degree angle, that when we compare the opposite side of that 48-degree angle to the hypotenuse of that triangle, that ratio we write will be equivalent to 0.74, which I would say that's roughly 0.75. So we could say the opposite of 48 degrees would be 3, and the hypotenuse would be 4, which 3/4 is roughly 0.75, just to give you an idea of what we're saying here. And so that any right triangle that has a 48-degree angle, when you compare the opposite side to the hypotenuse of that triangle, its ratio will always be 0.74. So just to give you some context here, we're not just plugging in numbers, we're seeing how all this works in this idea of similar right triangles. Now they want us to evaluate tangent of 65, cosine of 12, and sine of 90. So let's run over to Desmos and calculate those. So the tangent of 65, we'll just simply start typing TAN, 65. We'll round that in just a moment. The cosine of 12, so COS for cosine, 12. And last, the sine of 90. So the tangent of 65 rounded to the nearest thousandth. Again, the 100th, this first 4 is in the hundredths place. So we look to the 4 right behind it, and that 4 tells us to, of course, round down or stay the same. So the tangent of 65 will be 2.14, roughly. The cosine of 12, the 7 is in the hundredths place. So the 8 actually tells us to round the 7 up. So it would be 0.98. And last, we saw something rather interesting here. The sine of 90 degrees is just 1. So before we run into item 3, let's think about why this unique angle measure, or why this unique ratio is just 1, the sine of 90 degrees. Well, if we think about it, let's say that here we have this 90-degree angle. The sine ratio is the opposite side compared to the hypotenuse, which the opposite side of the 90-degree angle would actually be the hypotenuse. So whatever measure it was, let's say it's 3. If we write the sine of 90, we would be writing 3/3. Or if the hypotenuse was 6, well, the opposite of that 90 degree would be 6, and then the hypotenuse of that triangle would be 6. It would be 6/6, which is 1. So unique idea here, and again, I love to put it back in context. We're not just evaluating just some random numbers here. We're putting it in the context of right triangles. Now let's take a look at item 13, writing each ratio in simplest form. That's very different than writing it in decimal form, rounding each value to the nearest hundredth. We are writing it in simplest form. So looking at x initially as our indicated angle, this is the sine of x. Opposite of x is 36. And the hypotenuse, again, regardless of which angle we're looking at, the hypotenuse is going to be 45. So the sine of x is going to be 36 over 45, which can actually be reduced because each of these numbers can divide evenly by 9, so they'll be reduced to 4/5. Anything peculiar about these two numbers we just saw in our lesson? Now let's take a look at the cosine of x, which is the adjacent side to x, which in this case would be xz, which is 27 in length. So we would compare 27, the adjacent side, to the hypotenuse, which would be 45, so 27 over 45. And yes, these two can reduce just like they did on the sine of x. These two can reduce to 3/5. Again, we've already seen this ratio in a previous diagram. Now, before we even attempt to look at the sine of y, let's recall something that the book tried to make very clear to us. The sine and cosine of complementary angles are equal. So, if we found that the cosine of x is 3/5, then the sine of y also has to be 3/5. And we'll prove that here. So the sine of y, now looking at y as the indicated angle, the sine of y, opposite of y, is xz, which is 27, which we see here, compared to the hypotenuse, which is 45. So the sine of y would have been 27 over 45, but we already know that's going to simplify to 3/5. And likewise, the cosine of y, I'll go and show that these two are equivalent. The cosine of y is equivalent to the sine of x. So without actually solving or, maybe writing opposite or adjacent or switching it around, we know that the cosine and sine of complementary angles are equivalent. So the cosine of y is also 4/5. Now we do need to take an opportunity to find what the tangent of x is, which, remember, tangent, that ratio is opposite side over adjacent. So opposite of angle x is line zy, which is 36. Compared to the adjacent side, which is 27. And just like it reduced up here, it's probably going to reduce the same way, both divisible by 9. So 36 divided by 9 is 4. 27 divided by 9 is 3. So the tangent of x equals 4/3. Now, I did draw a conclusion that the book didn't make. The tangent of x and the tangent of y aren't equal. They are reciprocals to one another. And that's because, depending on which angle you're looking at, it switches, right? Opposite of x is 36, but opposite of y is 27. So the roles of opposite and adjacent actually switch depending on which angle you're looking at, which that's what the ratio tangent is, the opposite to the adjacent. So if the tangent of x is 4/3, the tangent of y is 3/4. Now let's take a look at item 14. Item 14 is designed just to enhance our understanding of what we're actually doing when we say sine, cosine, and tangent. We're writing ratios of different sides of right triangles. So number 14, it says, Elena was asked to write an explanation of how to find the tangent of P. She wrote, to find the tangent of angle P, I found the ratio, that's good, of the length of the sides opposite of angle P, that's good, to the length of the side adjacent to angle P. That sounds good too. And so she compared the opposite side of angle P to the adjacent, and that is the definition of tangent. Since these sides have the same length, she found that the tangent of P equals 1 foot. Critique Elena's statement. Is there anything she should have written differently? If so. Now, what we're exploring here when we say the sine, cosine, and tangent is we aren't specifically saying that the sine of x is, in this case, 4/5 feet or 4/5 inches. We're just saying if we had any right triangle that had the same measure as x, then the opposite side compared to the hypotenuse, that ratio would always be 4/5. Not necessarily the actual measurements are 4 and 5. Notice here in this diagram, the measurements aren't actually 4 and 5. It's just the ratio of the opposite side of x, 36, to the hypotenuse can be reduced in simplest form to 4/5. So when she makes the claim that the tangent of P is 1 foot, she's kind of stepping out of line. She should have simply said that the tangent of P is 1. Sine, cosine, and tangent aren't actually written in units of measure like we do when actually measuring in inches or feet or miles or yards or anything like that. We're saying that if there's any right triangle that has the same measure of angle P, then the opposite side when compared to the adjacent side will be 1. So we could have any right triangle that's similar to triangle PQR, and the opposite side when compared to the adjacent side will always be 1. Not necessarily their lengths are 1. And that's what she got confused here. Again, back here we said that the sine of x was 4/5. That's not the measure of the opposite side compared to the adjacent. The opposite side was 36 and the hypotenuse, or excuse me, opposite to hypotenuse, the opposite side was 36 and the hypotenuse was 45. 4/5 wasn't the measure. We're saying that opposite of x when compared to the hypotenuse will always be reduced to 4/5. So let's make sure when we're writing sine, cosine, and tangent, we're not writing those in units of measure. So that is the end of lesson 22-2 practice. Hope that helped. Thank you all for watching.